In this tutorial, I will show you how to translate hydrogeological problem formulation into the conceptual model description, and how to build and run steady-state groundwater model using processing MODFLOW. Here, problem formulation given for us, and the problem formulation said as an aquifer system with two stratigraphic units is bounded by impermeable geological formation, which is granite to the north and south. And you can see here on the figure, the north boundary is granite geological formation, and also the south boundary is granite geological formation. Both geological formation are impermeable geological formation. The west and east side are bounded by river, which are fully hydraulic contact with the aquifer. Here the east boundary is river, and also the west boundary is river, and this river is fully hydraulic contact with the aquifer. The water level in the river on the west and east boundary are 9 meter and 8 meter above reference level. So here the water level in this river is 9 meter, and the water level in the east boundary is 8 meter. The aquifer system is unconfined aquifer and also isotropic. You know what I mean by unconfined aquifer. Unconfined aquifers are aquifer which have no confining layer from the top, and the upper portion of the aquifer is water table, and it is isotropic. That means hydraulic property of the aquifer, hydraulic property of the aquifer is isotropic. The horizontal hydraulic conductivity of the first and second stratigraphic unit is given for us, and the hydraulic conductivity of first stratigraphic units is 0.0001 meter per second, and that of the second one is 0.005 meter per second respectively. The vertical hydraulic conductivity of both units is assumed to be 10% of horizontal hydraulic conductivity. Effective porosity is also given for us, which is 0.25%. Elevation of ground surface, that is top of the first stratigraphic unit, is 10 meters. So the thickness of the first plus second stratigraphic unit is 10 meters. The thickness of the first and the second unit is given for us, which is 4 meter and 6 meter respectively. The constant recharge rate of 8 times 10 raised to minus 9 meter per second is applied to the aquifer. A pumping well is situated in the center of the aquifer, so there is a pumping well here, and this pumping well is at the center of the aquifer, and the pumping rate is this value, and from the lower 3 meter over the second stratigraphic unit. Here the main objective of this web lecture is to show you how to determine the hydraulic distribution in the aquifer in the case of what? Steady state condition, steady state groundwater flow condition. In groundwater flow modeling, first we have to have conceptual model. So here we have conceptual model choice. The model will be steady state model, since no time dependent stress factor are presented there. All parameters given for us are not time dependent, including recharge and also pumping rate. All are constant through the time. 3D model, since different stratigraphic units are presented there, we have two stratigraphic units, stratigraphic 1 and the stratigraphic 2. The stratigraphic 1 having thickness of 6 meters and the stratigraphic 2 having thickness of model dimension is model dimension. You can see model dimension, which is 580 meter by 680 meter. You can see the model thickness on the figure. Model thickness of 10 meter corresponds to the aquifer thickness. The aquifer thickness is 10 meters, so the model thickness will be also 10 meter. Grid cell of the cell is 20 by 20. Actually, while selecting the grid cell of the model, we have to compromise accuracy and computation time. When we select a small size of grid cell, the accuracy may be good, but the computational time may be long, so we have to compromise both accuracy and computational time. For current, it's better to select this value 20 meter by 20 meter. Layer thickness of 4 meter for the first unit and 2 times 3 meter for the second unit. This is because the well, pumping well is what? Situated at what? The lower 3 meter of the second stratigraphic unit. So we have to divide the second stratigraphic unit into 2 layers. Top layer is unconfined aquifer and other 2 layers are what? Confined aquifers. You know what is confined aquifer and what is unconfined aquifer. In the case of confined aquifer, there is some confining layer from the top and layer from the bottom. For unconfined aquifer, the uppermost saturated layer is water table, and there is no confining layer there. And here, some parameters are also given for us. Hydraulic conductivity is given for us, porosity is given for us, and you can look at the value of porosity and hydraulic conductivity, both vertical and horizontal hydraulic conductivity. Boundary condition is also given for us. No flow boundary condition at north and south. You can look at the north boundary is granite formation and south boundary is also granite formation, granite rock. Both are impermeable geological formation. Fixed head boundary at the east and west boundary, since the rivers are in full hydro contact with the aquifer. So this one is fixed head boundary, this one is fixed head boundary. Both west and east boundary are what? Fixed head boundary, having constant head. No flow boundary at the model bottom. That means the bottom of the model is what? The model is basement rock. There is no flow of water from the aquifer to the bottom. Constant recharge boundary at the top, which is equal to this value, which is equal to 8 times 10 to the power of -9. And we have also pumping or well boundary of this rate. Let's start with modeling. First, we have to save our model. To save our model, we have to click File, then New Model. Let us save our model here in PM tutorial and name tutorial 1. Save. Once we save our model, the first step is what? Generating the grid. To generate the grid, we have to click here on the grid, then mesh size. Number of layer we have is 3 layer. We have 3 layers, so we have to specify as 3. Model thickness is what? 10 meter, which is equivalent to the thickness of aquifer, and the model top elevation is also 10. And also we have to specify number of row and the number of column. You can look at conceptual model, and the grid cell is 20 meter by 20 meter, and the extent of our model is 600 by 580. So if we divide 600 by 20, we can get 30 cell. So 30 column by 30 row. So we have to specify row as 30 and column also 30. The model extent 600, model extent 600. Actually, model extent of row is 580. For simplification, it's better to make it 600. And also we have vertical exaggeration. We have to specify vertical exaggeration, and when we increase the value of vertical exaggeration, then the results of the model, the thickness of the vertical thickness of the model will increase, and it can increase the clarity of our result. For the time being, it's better to use the default value of 20. Then okay. Then leave it there. Then yes. The next step is what? We have to specify layer property. Layer property. What is the first aquifer? The first aquifer is unconfined aquifer. And the second aquifer, the second layer is confined layer, and the third layer is confined layer. So we have to specify like this. Then okay. We specify the first layer as unconfined aquifer because the problems formulation and conceptual model also say that it is unconfined aquifer. Okay. Next step, we have to assign cell status for each cell. To specify cell status, we have to click on grid, then cell status, epoch. Then here we have to specify cell status of each cell. Here you have to know how we specify cell status. When we say cell status is 1, that means the cell is active. When we say this -1, that means the cell having constant heat. When we specify as 0, that cell is what? Inactive. That means there is no flow. Okay. In our case, we have constant heat boundary at west boundary and east boundary. So those cells should be what? Constant heat, and their value should be -1, and all other cells should be what? Active cell. So when you click on each cell, you can see this value. That means all cells are active for the time being by default, and we have to change the north boundary, the cell status of the north boundary as constant heat. And to do that, we have to click here on this cell and right click, and we have to specify as -1. Then okay. So the cell status of this cell is what? Constant heat. And we have to do the same for all cells in the west boundary. To do that, you have to click here on this button which says switch cell by cell duplication on. Then drag like this. In this case, all cells in the waste boundary are what? Constant. And we have to do the same thing for all cell in the east boundary. Now we assign the cell status of first layer. You can look here, the first layer. And we have to do the same thing for second layer and third layer. To do that, we have to copy the status of the first layer to the second layer, the status of second layer to the third layer. The status of the cell status of the first layer, third layer, and the second layer are the same in our case per the problem formulation. To copy the status of the first layer to the status of the second layer, we have to click on switch layer or cross section copy all, and then click this button. Now the status of the first layer is copied to the status of the second layer, and we have to do the same for the third layer. Click this one. Now we already specify, or we already assign the status of what? All layer in the first layer, in the second layer, and the third layer. So we have to save our input. To do that, we have to click here on leave editor, then save change to cell status. Yes. Then the next, we have to specify the top layer elevation and the bottom layer elevation. To specify top of layer elevation, we have to click on top of layers and click no. Then we have to specify the top elevation by clicking value, then reset matrix 10. Actually the thickness of the aquifer is 10, and also the top elevation of the first layer is 10. And we have to do the same thing for second layer. What is top elevation of second layer? Top elevation of second layer is equal to 6. So we have to specify like this. Okay. What is the top elevation of third layer? The top elevation of third layer is 3 meters, because the pumping well is stand on what? The third layer, and the thickness of the third layer is what? 3 meters. So it is top elevation should be 3 meters. Okay. Then leave it there. Then yes. We have to specify also the bottom elevation of each layer. To specify the bottom elevation of each layer, we have to click on grid, then bottom of layer. And this window is pop up. The aquifer top elevation has been specified. That is what we have been done. And the software by itself can use that value to assign the layer bottom elevation. So we can say yes and leave it there and accept it. Then the next procedure is what? Specify the initial and prescribed hydrolocate. To specify initial prescribed hydrolocate, to click value, reset matrix, and while specifying initial and prescribed hydrolocate for the model, it is better to assign initial and prescribed hydrolocate equal to the thickness of the model. So let us do that. What the thickness of the aquifer? Thickness of the aquifer is equal to 10. So okay. However, we know that the initial hydrolocate of west boundary is 9 and initial hydrolocate of east boundary is 8. So we have to specify that one. To specify it, we have to click here on this cell, right click, then specify 9 and okay. and we have to drag this value to all cell in the west boundary. To drag it, we have to click on this button, then drag this value. And we have to specify the initial prescribed head of what? The east boundary, because it is now we have a constant head of 8. So we have to specify this one. Then okay. Then we have to copy this value to all cell, or we have to duplicate it to all cell in the east boundary. Okay, we define or specify initial and prescribed hydraulic head of what? First layer. And we have to do also for the second layer and the third layer. In our case, initial prescribed hydraulic head of first layer is equal to initial hydraulic head of second layer equal to initial hydraulic head of what? Third layer per problem formulation. So we have to copy the value given for the first layer to the second and third. To do that, we have to click here on switch layer or cross section, copy on, then click this button and this button. Okay. Now initial and prescribed hydraulic head of first layer is copied to the second and the third, and initial hydraulic initial and prescribed hydraulic head is already specified for all layer. So we have to click this leave editor, then yes. The next procedure is what? Specifying horizontal hydraulic conductivity. We know horizontal hydraulic conductivity of first layer. Horizontal hydraulic conductivity of first layer is this value, and horizontal hydraulic conductivity of second layer and third layer is this value. Let us specify this. To specify horizontal hydraulic conductivity, you have to click here on horizontal hydraulic conductivity and value reset matrix. By default, horizontal hydraulic conductivity of first layer is equal to 0.001, and this value is the same to the value here given in our location, so we have to accept this one. Okay, we have to do the same thing for second layer, and we have to click on value reset matrix, but in this case horizontal conductivity of second layer is not 0.001, it is 0.005, so we have to specify like that, and okay. And we have to do the same thing for third layer. Horizontal hydraulic conductivity of third layer is equal to 0.005. Then okay. Leave editor. Yes. We have to specify also vertical hydraulic conductivity. Specify vertical hydraulic conductivity. Click vertical hydraulic conductivity. Then value reset matrix. Vertical hydraulic conductivity is 10% of horizontal hydraulic conductivity, so this value is equal to 10% of horizontal hydraulic conductivity, so accept. And let us specify for second layer, click here, then value reset matrix. Let us change this value to 0.00005. Then okay. For third layer also, value reset matrix 0.0005 meter per second. Okay. Then leave it as save change to vertical hydraulic conductivity. We specify initial prescribed hydraulic head, horizontal hydraulic conductivity, vertical hydraulic conductivity. What's left? Effective porosity is left. So let's click on effective porosity, specify effective porosity, value reset matrix. The default value of effective porosity given to the model is equal to here effective porosity given in the problem formulation. So we have to accept this default value, accept. And let us check for second layer. Second effective hydroconductive effective porosity for second layer is also 0.05. Effective porosity of third layer is also 0.25. So we have to accept that this is. Then leave it there. Then yes. Another parameter we have is what? Recharge. So we have to what? Specify this one also. Recharge. To specify this recharge, we have to click here on model, then flow simulation, then flow package, then recharge. And recharge is what? To the first layer, only to the first region. This precipitation, and the precipitation is from the top, and it is to the first layer. So we have to specify that recharge value to the first layer. Here you can look at the layer number, this first layer. Value reset matrix. What is the value of recharge rate? The value of recharge rate is what? 8 times 10 to the power of minus 9. So we have to write like this. 8 exponent of minus 9. Then okay. Then leave, save change to recharge. The only left given value is pumping rate, and this pumping well is situated at the center of aquifer from the lower 3 meter of what? Second stratigraphic unit. So we have to put this pumping well in the third layer. Well, then we have to go to third layer. You can look here, and the well is what? At the center of the aquifer. At the center of the aquifer. That means, well, the dimension of the model, the dimension of our model is what? 30 by 30. So the center is around here, which is about 50 by 50. And we have to click this, say on this cell, then right click and specify the value of what? The value of pumping well. And the value of pumping well is equal to minus 0.0012. Here, this value should be negative because the aquifer is losing water. It is pumping well, not injection well. So the value should be negative. Then okay. Leave it there. Then yes. We already specify all parameters given for us. So the next procedure is what? We have to run our model. To run our model, we have to click on MODFLOW, then run the model. Then this window will pop up. Then okay. Then click any key on keyboard. Then black window will disappear. Then we can visualize our result. To visualize our result, you can visualize 2D visualization. Using 2D visualization, you can visualize our result using 3D visualization or water budget and so on. Let us visualize our result using 2D visualization. And what was our objective? The objective was to determine hydrolicate distribution in the aquifer. So we can see hydrolicate distribution in the aquifer by clicking OK. And this one is what? Hydrolicate distribution in the first layer. You can click this one also. You can see hydrolicate distribution in the second layer, and click this one and see hydrolicate distribution in the second and third layer. we can decorate our hydraulic heat map using option, then environment. We can change contour property. We can change the interval of our contour. We can change also the color spectrum of our contour. Let us change this color to red, then okay. So the minimum spectrum is what? This color, which is pink, and the maximum one is what? Blue, then okay. And we can also change label format. We can use fixed number, or we can use exponential label. Okay, then okay. So you can see the hydraulic head distribution map for third layer, second layer, and first layer. Let me add one thing for you. Let us see water budgets of our model. To see water budget of our model, we have to click on tool, then water budget, and the straight period is 1, or it is steady state. Time step is also 1, it is steady state. And let us define sub-region. We have 3 sub-region because we have 3 layers: layer 1, layer 2, layer 3. Define sub-region. Let us define layer 1 as sub-region 1. So value reset matrix, it has 1, sub-region 1. For layer 2, let us define it as what? Sub-region 2. Sub-region 2. Okay. Let us define layer 3 as sub-region 3. Sub-region 3. Then okay. Then leave editor. Then yes. Then okay. Okay. Then click any key on keyboard. Then this value will pop up. This is what? Water budget of what? Our model. Water budget of layer 1, water budget of layer 2, water budget of layer 3. Or you can see region 1, which is layer 1, region 2, which is layer 2, region 3, which is layer 3. Let us see water budget of what? Each layer. Look at layer 1 or region 1. This amount of water is what? Flow from, this amount of water is flow from river to this aquifer or layer 1. And this amount of water is flow out of layer 1 to the river. So in this case, there is negative exchange. And we have also another flow, which is lower flow. That means this amount of water is what? Flow from aquifer 1 to, or from layer 1 to layer 2. So still layer 1 is what? Losing water. And we can see also for layer 2 and layer 3. And you can look at the water budget data in close and rectify or report your data using this output. Thank you for your attention.